percentage, it always adds up to 100%. So we're going to look at a problem determining the mole fractions and the partial pressures of a series of gases in a mixture. So it's best to look at each of these individually. We have carbon dioxide, methane, and helium. And we want to know what is the pressure of each and what is the mole fraction of each. So we'll start off with the carbon dioxide. Okay, carbon dioxide, I have 0.250 moles. My methane, I have 1.29 moles. And my helium, I have 3.51 moles. So if I look at this and I add them all up, the total amount of gas is equal to 5.05 moles. So now, if I know the total number of moles, I can calculate the mole fraction of each of these gases. So carbon dioxide, I have 0.250 moles. I'll divide that by the total, 5.05, and that is equal to 0.0495 is my mole fraction, and we call it X. So it's my mole fraction of carbon dioxide. Now I can do the same thing for methane. 1.29 moles of methane divided by 5.05 moles gives me a mole fraction of methane of 0.255. And I'll do the same thing for helium. 3.51 moles divided by 5.05 moles is equal to a mole fraction of 0.695 for my helium. So I now know the mole fraction, and now I'm trying to find the partial pressures of each of these things in the mixture. So when we look at this, if we know the total pressure and we know what fraction of the gas molecules each gas represents, we can do this very simply. It's kind of like a proportion. So we can say the pressure of carbon dioxide is equal to the mole fraction of carbon dioxide times the total pressure. So we plug this in and we get 0.0495, my mole fraction of CO2, times my total pressure, 5.78 atmospheres. So my pressure of carbon dioxide is equal to 0.286 atmospheres. Now I do the same thing for the remaining gases. The pressure of methane is equal to the mole fraction, 0.255, times the total pressure, 5.78 atmospheres, and that's equal to 1.48 atmospheres for methane. And I'll do the same thing for helium. The pressure of helium is the mole fraction of helium, 0.695, times the total, 5.78 atmospheres, is equal to 4.02 atmospheres for helium. So we can use mole fraction to get information about pressure fraction, or the pressure of one of the components. Now, there's one for you to try on the next page, doing a similar sort of thing. So go ahead and pause the video, work that problem out, and then you can restart the video to look at the solution. Okay, on this one you had a little bit more thinking that you had to do, because this gave you information about the mole fraction of xenon, but it didn't tell you anything about the mole fraction or the moles of neon. So the first thing we had to do is to determine information about the neon by thinking that the mole fraction of neon will be 1 minus the mole fraction of the xenon. So that's equal to 1 minus 0.761 is equal to 0.239 which is the mole fraction of neon. Now, we know the mole fractions. Now we want to know the total number of moles of each gas in a 15.75 liter vessel at 30 degrees. So we kind of have to go backwards. We know the total pressure. That will allow us to determine the partial pressure of each gas. Once we know the pressure of each gas, we can find the number of moles of each gas. So I started with neon. The mole fraction of neon, 0.239, times the total pressure, 6.50 atmospheres, is equal to 1.55 atmospheres. Now, I know the ideal gas law, PV equals nRT. So I decided to rearrange to solve for the number of moles of neon. N is equal to PV over RT. My pressure was 1.55 atmospheres. That's just the pressure of the neon. My volume, 15.75 liters. A gas constant, 0.0821 liter atmosphere per mole Kelvin, times the Kelvin temperature. My 30 degrees Celsius is 303.2 Kelvin. So the moles of neon is 0.981. Now I'm going to do the same thing for the xenon. This time I'll use the mole fraction of the xenon. So my mole fraction of xenon is 0.761 times the total pressure, 6.50 atmospheres, is equal to 4.95 atmospheres. I know PV equals nRT, so N equals PV over RT. My pressure, 4.95 atmospheres, times my volume, 15.75 liters, divided by my gas constant, 0.0821 liter atmosphere per mole Kelvin, times 303.2 Kelvin. And I get 3.13 moles of xenon. So that concludes this video. The next video will be collecting gases over water and additional problems.